We'll start in about 1 minute. Today we'll cover section 8.3 on rational exponents. And if there's time, we'll review some of the chapter 7 material. Test 3 will be on Friday, April 10th, next week. Okay, so we'll start with section 8.3. Section 8.3 on rational exponents. Radicals can be written in rational exponent form. A rational exponent is an exponent that is an ordinary fraction in lowest terms. And the properties of exponents that we learned in section 5.2 apply to rational exponents. And here's our definition. This is how we convert radicals to rational exponents. So in this definition, let n be a positive integer. Then the nth root of a is equal to a raised to the exponent 1 over n. So in the exponent, note that the denominator of the exponent is n, and that is the same number as the index of the radical. We'll convert a few radicals to rational exponent form. The square root of x, remember that the square root is a radical with index 2. So when we convert the square root of x to rational exponent form, we just write x to the 1/2. The exponent is 1/2. In the next example, the third root of 15, or the cube root of 15, the index is 3. So we can write this as 15 to the exponent 1/3. The denominator of the exponent is 3. That's the same number as the index of the radical. The fourth root of n, converted to rational exponent form, that this is n to the 1/4 power, or n raised to the exponent 1/4. The fifth root of 11, the index is 5, so this is equivalent to writing 11 raised to the exponent 1/5. We'll look at some examples where we do the opposite. We have some terms that are in rational exponent form, and we'll convert them to radical form. 17 to the 1/2, when we convert this to the radical form, we can write the radical. The denominator of the exponent is 2, so that means the index of the radical is 2, and then we put the number 17 inside the radical. Of course, this is the same as the square root of 17, and so it's not necessary to write the index 2 for a square root. The next example, a to the 1/4. The denominator of the exponent is 4. When we convert it to radical form, the index of the radical is 4, the same as the denominator of the exponent. And then on the inside, we just put a, the 4th root of a. 29 to the 1/6. Converted to radical form, well, you can write the radical. The denominator of the exponent is 6, so that's the same number as the index. And then the base number, 29, is inside the radical, the 6th root of 29. Y to the 1/3. In radical form, this is a cube root of y. Okay, we'll simplify some expressions that have rational exponents. It's okay if you convert them to radical form first, but I'll show you that it's not necessary in these examples to convert them to radical form. 49 to the 1/2, that is equivalent to the square root of 49. And the square root of 49 is just 7. If you want to convert 49 to the 1/2 to radical form, you can. The square root of 49, we know is 7. So either way, you get the same result, 7. In the next example, 81 to the 1/4. That is the 4th root of 81. 81 is a perfect 4th power. 3 to the 4th power is 81. So 81 to the 1/4 simplifies to 3. I'll show you on this one an alternative way to determine what 81 to the 1/4 is, besides converting it to a radical form. 81 to the 1/4. Well, 81 is 3 to the 4th. So 81 to the 1/4 is equivalent to 3 to the 4th, and that is raised to the 1/4. If you remember one of the properties of exponents from section 5.2, if you have something raised to an exponent, and that entire expression is raised to an exponent, you can multiply those two exponents. And 1/4 times 4 is 1. So this just simplifies to 3 to the 1st, or 3. The property of exponents that I applied there, I'll just remind you, if you have a to the m raised to the power n, then you can multiply the exponents m times n and write it as a to the m times n. This is just showing you an alternative way to simplify 81 to the 1/4. The next one, 32 to the 1/5. I'll write this in radical form first. It's not necessary, but I'll just write it as the 5th root of 32. You might remember that 32 is a perfect 5th power, because 2 to the 5th is equal to 32. So the 5th root of 32 simplifies to 2. Okay, and the final example on this page, 64 to the 1/3. It turns out that 64 is a perfect cube, or a perfect 3rd power, because 4 to the 3rd is 64. So 64 to the 1/3, let's write a little bit more detail on this one. It's more detail than is necessary, but recall that 64 is 4 to the 3rd. And so 64 to the 1/3 is equivalent to 4 to the 3rd to the 1/3. And then if you apply this property of exponents that I wrote down here, we can multiply the exponents. 1/3 times 3 is 1. And so it simplifies to 4 to the first power, or 4. Okay, we'll move on to another definition involving radical form converted to rational exponent form. This one's a little more involved than this basic definition. Okay, so this time we let m and n be positive integers. Then the nth root of a raised to the power m is equal to the term a to the m raised to the 1 over n. This is just an application of the definition that we saw on the first page. All we're doing is raising the radicand a to the m to the exponent 1 over n when we convert from radical form to rational exponent form. Then using that property of exponents that I wrote down earlier, a to the m raised to the 1 over n is a to the 1 over n times m, or a to the m over n. Then using a property of exponents again, the same one, in fact, m over n is also equal to m times 1 over n. So we can write this, if we want to, as a to the 1 over n in parentheses raised to the power m. And then on the inside, if we convert a to the 1 over n to radical form, that's just the nth root of a. And then we raise that nth root of a to the power m. These 5 expressions are equivalent. We will use them to our advantage. Sometimes using one of those forms is more of an advantage than the others. Okay, so we'll practice converting radicals to rational exponent form. This one, the 7th root of x to the 4th. Well, the radicand is x to the 4th. The index of the radical is 7. So I can put in parentheses x to the 4th and then raise that to the 1/7 power, because the denominator of the exponent is the same as the index of the radical. And then we can apply that property of exponents that we reviewed a few minutes ago, x to the 4th raised to the 1/7. If we multiply 1/7 times 4, we just get x to the 4/7. Okay, the next one is a little, I don't know if I should say tricky, but something that you have to be aware of. Convert the 4th root of 2y to rational exponent form. Okay, we start out the way we normally do. Inside parentheses, we put the term 2y, and then the exponent is 1/4. And inside the parentheses, think of 2 as 2 to the 1st power, and think of y as y to the 1st power. When the exponent is 1, you don't need to write it, but it's useful to remember that you could write it if you wanted to. And then if we apply another property of exponents that we learned from section 5.2, I can multiply the outer exponent 1/4 times each of those exponents. So I can write this as 2 to the 1/4 times y to the 1/4. 2 to the 1/4, well, if it's rational exponent form, it can't be simplified any further than that. So this is our answer if we're going to convert it to rational exponent form. Okay, the next example, convert the fifth root of 12w to the second to rational exponent form. Okay, so inside the radical we have 12w to the second, and so we raise that to the 1/5 power. And the coefficient 12, remember that's 12 to the first power, and then we can apply that property of exponents that says we can multiply the outer exponent 1/5 times each of those two exponents. And so we'll get 12 to the 1/5 times w to the 2/5, because 1/5 times 2 is 2/5. Okay, now we'll do some examples in the opposite order. We start with some expressions that are in rational exponent form, and we're going to convert those to radical form. Okay, so x to the exponent 3/4, the denominator of the exponent is 4. So we can just write the radical form directly by putting the index 4 and then x to the third on the inside of the radical. There is an alternative. It's not necessary, but if you want to first use a property of exponents and rewrite x to the 3/4 as x to the third to the 1/4, you can do that. That's what we saw in the definition that's higher up on this page that you can't see right now. But x to the third to the 1/4, when you convert that to radical form, well, the 1/4 means the index of the radical is 4, and then put x to the third on the inside. Either way, we end up with the same result. The next two examples, note that they sort of look similar. It's just that on the right, the term 5y is in parentheses, and this term in the middle, there isn't a set of parentheses around 5y. These mean two different things. So in this first one, 5 times y to the 2/3, the exponent 2/3 applies to y only. It doesn't apply to the coefficient 5. So we can write this in radical form. If we write 5 times, let's see, the index is the same as the denominator of the exponent. So the index is 3, and inside the radical we write y to the second. Okay, that's as far as we can go on this one. This one means something different than this one in the middle. Since 5y is in parentheses and the outer exponent is 2/3, the exponent 2/3 applies to y to the first, and it also applies to the factor 5 to the first. Okay, we're going to convert this to radical form. So on these kinds, you have to be careful, sufficiently careful. The denominator of the exponent is 3. So we can write the radical with index 3. And what you write down on the inside, well, it can be written in a couple of ways, but make sure that you apply the exponent 2 to the entire term 5y. So on the inside of the radical, this is an acceptable way to leave your answer in radical form. But on the inside, you can also square the term 5y. When you square the term 5y, that just means 5y times 5y, which is 25y to the second. A common mistake made in this situation is to put 5y without parentheses so that the exponent 2 would only apply to y, and that is an incorrect answer in this case. Okay, so watch out for that. Well, we'll evaluate some numbers with rational exponents. Okay, this one on the left, the number negative 16 is in parentheses and it's raised to the 1/4 power. Okay, so if you remember, if the index of a radical is even, so the denominator 4 is even, so this is equivalent. If you want to write it in radical form, you can. It's the 4th root of negative 16. In section 8.1, we discussed this type of situation. If the index of the radical is an even integer and the radicand is negative, like it is in this case, then it's not a real number. So for now, we just identify it as not a real number. It's a number, it's just not a real number. The next term means something different than the previous one. This is the negative of 16 to the 1/4. The exponent 1/4 applies to 16. This can be thought of as negative 1 times 16 to the 1/4. And the 1/4 applies to 16, but not to the negative 1. So this is a real number, the negative of 16 to the 1/4. 16 is a perfect 4th power. 2 to the 4th is 16. So this simplifies to negative 2 because the exponent 1/4 applies to 16, but not negative 1. Another way to write this, that it's not required, but you can think of this as the negative of the 4th root of 16. And the 4th root of 16 is 2, so this simplifies to negative 2. Okay, in the next example, this time we have 16 raised to the exponent negative 1/4. So remember what we do with negative exponents. We can write this as 1 over 16 to the positive 1/4. And then in the denominator, 16 to the 1/4 simplifies to 2. So this becomes 1/2. Okay, so 16 to the negative 1/4 is just a fancy way of writing 1/2. Okay, the next one, we also have a negative exponent, 32 to the negative 2/5. Okay, so let's write it as 1 over 32 to the positive 2/5. And remember that 32 is a perfect 5th power. So let's look at 32 to the 2/5 by itself. So I can point out a couple of things with this example. 32 to the 2/5. Well, we can think of this using properties of exponents as 32 to the 1/5, and we raise that to the power 2. And then properties of exponents, 2 times 1/5 is 2/5. But inside the parentheses, 32 to the 1/5 simplifies to 2, because 32 is a perfect fifth power. So 32 to the 1/5 is 2, and then 2 to the second is 2 times 2, or 4. So this 32 to the negative 2/5, which is 1 over 32 to the positive 2/5, that simplifies to 4. Whoops, sorry, it simplifies to 1 over 4. Okay, in the next page, we're going to practice some of the properties of exponents with some terms that have rational exponents. Okay, so this says apply the properties of exponents to the expressions with rational exponents. Do not convert to radical form unless the directions call for that. Okay, so this first example, x to the 1/6 times x to the 4/3. Up here, I'll write the property of exponents that we're going to apply on this one. If you remember, if you have something like a to the m times a to the n, if the bases are the same and you're multiplying, you can write the base and add the exponents, m plus n. We learned this in section 5.2. We're going to apply this property to this situation. X to the exponent 1/6 times x raised to the exponent 4/3. We can write this as x to the 1/6 plus 4/3. And then we just add the fractions. Before we can add fractions, we have to have a common denominator. The least common denominator is 6. So this is x to the 1/6 plus 8/6. And now that the denominators are the same, we can add those two fractions. 1/6 plus 8/6 is 9/6. And we want to write fractions in lowest terms. So the exponent 9/6 simplifies to 3/2. So our simplified answer is x to the 3/2. In this next example, x to the 6th is raised to the exponent 4/3. So we've seen the property that applies to this a few times already today. We're just going to multiply the exponents, 4/3 times 6. Okay, so x to the 6 times 4/3. Well, you can go about it in a couple of ways. If you just multiply 6/1 times 4/3, then it's x to the 24/3. And then 24/3 simplifies to 8. So our simplified answer is x to the 8th. Okay, the next example, x to the 2/3 divided by x to the 5/3. At the top of the page, I'll remind you of the property that we're going to apply here. If you have a to the m divided by a to the n, This can be written in one of two ways. It can be written as a to the m minus n. And this one means that we could write it as a fraction with a denominator of 1, but it's not required. But it might help you remember. An alternative way, a to the m divided by a to the n, is 1 over a to the n minus m instead. Whichever of those two you pick, doesn't really matter as long as you know the appropriate properties of exponents. Okay, so we'll apply that property to this one. So we can write it as, since we have x to the 2/3 divided by x to the 5/3, we can write it as x to the 2/3 minus 5/3. And 2/3 minus 5/3 is negative 3/3. So this is x to the negative 3/3. But negative 3/3 is just negative 1, so this is x to the negative 1. If you remember, we don't want our final answer to have any negative exponents, so we can replace x to the negative 1 with 1 over x to the positive 1, or just 1 over x. Okay, that's a perfectly fine way to get the simplified result. But if you want to try it the other way, we can write this as 1 over x to the 5/3 minus 2/3. And then 5/3 minus 2/3 is 3/3, so we get x to the positive 3/3. But 3 over 3 is 1, so we just get 1 over x. So you see, either way you choose to go about it will get you to the end result. You just need to apply the appropriate properties at the appropriate times. Okay, the next example, the property that we're going to apply, this one has been applied already. But at the top, I'll write what we're doing. If you have a times b in parentheses, and if you have an outer exponent m, then think of this as a to the first times b to the first. And so you can multiply the exponent m times each of the exponents and get a to the m times b to the m. Okay, we're going to apply this property to this example. Inside the parentheses, we have x to the 3/4 times y to the 1/2, but that product is raised to the exponent 2/3. So when we apply the outer exponent, we're just going to multiply it by each of those two exponents. So we get x to the 3/4 times 2/3 times y to the 1/2 times 2/3. And then we just do the arithmetic on the fractions. So 3/4 times 2/3, well, you can think of that as 6 over 12, which simplifies to 1/2. So x to the 1/2. And then y to the 1/2 times 2/3. 1/2 times 2/3 is 2 over 6, but that simplifies to 1 over 3. Whoops. This is supposed to be a y to the 1/3. Okay, the next example, 32 times x to the 1/3 raised to the exponent 3/5. Okay, so think of 32 as 32 to the first. So when we apply the outer exponent, we'll get 32 to the 3/5 power. And then we're going to multiply the exponent 3/5 times 1/3, and we get x to the 1/3 times 3/5. Well, this is going to work out nicely because we saw this type of thing earlier today already. 32 is a perfect fifth power, and the denominator of the exponent is 5. So we can rewrite 32 to the 3/5 as 32 to the 1/5 raised to the 3rd. And then we can go ahead and simplify x to the 1/3 times 3/5. That's going to simplify to x to the 1/5 because 3 over 15 reduces to 1/5. And then inside the parentheses, 32 to the 1/5 simplifies to 2 because 32 is 2 to the 5th. So this becomes 2 to the 3rd times x to the 1/5. And of course, 2 to the 3rd is just 8. So our simplified answer in rational exponent form is 8 times 1/5. Keep in mind, though, that in this final answer, the exponent 1/5 applies to x only. It does not apply to 8. Okay, the next example, 343 to the exponent 2/3. Well, try to remember that almost everything works out pretty nicely in this class. So 343 is a perfect cube or a perfect third power. 7 to the 3rd power equals 343. Okay, so we can rewrite this as 343 to the 1/3 and then raise this all to the exponent 2. And you can verify that we're doing it correctly. 2 times 1/3 is 2/3. And the cube root of 343 is 7 because 7 to the 3rd power equals 343. So this simplifies, well, the next step is 7 to the 2nd, and then 7 to the 2nd is just 49. Okay, we covered the material from section 8.3, and so in the remaining 12 or 13 minutes, I'll look at some of review problems from chapter 7. So if you remember, on April 10th, Friday, we have our test 3, which will be over chapter 7 and chapter 8 material. Okay, solving equations with rational expressions. This is from section 7.4. This is a type of problem that a lot of students need practice. Okay, well, when solving rational equations with rational expressions, we want to be aware of the restricted values. So one of the restricted values is 3, because x minus 3 is in the denominator. So I'll just write down the restricted values over here. X is not permitted to be 3 because that makes this denominator 0. The other denominator, x minus 2, that denominator is 0 when x is 2. So another restricted value is 2. X cannot be 2. Note that x squared minus 5x plus 6 is just the product of x minus 3 times x minus 2. And so the least common multiple of the denominators, which we need to solve the equation, the least common denominator in factored form is x minus 3 times x minus 2. In expanded form, it's just x squared minus 5x plus 6. Okay, so what we do, we multiply every term on both sides of this equation by the least common denominator. And we can use the factored form or the expanded form, whichever is the most useful. So I'm going to use the factored form when I multiply the two terms on the left side of the equation. But when I multiply the right-hand side by the least common denominator, I'm going to use the expanded form. Okay, so the first term, we multiply this by, I want to make sure I have enough space. So x minus 3 times x minus 2. If it helps, you can think of this as having a denominator of 1. And we're going to multiply that by the first term, x minus 2 over x minus 3. Then we're going to multiply the least common denominator by the second term, x minus 3 over x minus 2. So once again, I'll use the factored form, x minus 3 times x minus 2 over 1 times the term x minus 3 over x minus 2. And then on the right-hand side, I'll use the expanded form of the least common denominator, x squared minus 5x plus 6 over 1 multiplied by 2x squared over x squared minus 5x plus 6. Okay, it looks worse before it looks better, but the payoff is worth it. In this first product, the x minus 3 factors cancel, one from the numerator, one from the denominator. And so we're just going to be left with x minus 2 times x minus 2. And then in the next product, the x minus 2 factor from the numerator divided by x minus 2 in the denominator. Well, a number divided by itself is equal to 1, and we're just left with x minus 3 times x minus 3 in this case. And on the right-hand side, we get a cancellation, x squared minus 5x plus 6 divided by itself equals 1. And all we're left with on the right-hand side is 2x to the second. Okay, so this equation looks simpler to solve, but we have to multiply the binomials, combine like terms, and then see what we have. When we multiply x minus 2 times x minus 2, we're going to get x squared. I'll go ahead and write it out. X squared minus 2x, and then another minus 2x, and then negative 2 times negative 2 is plus 4. And then we add that to the product of the next two terms, which is x to the second, and then minus 3x, and minus 3x again. And then negative 3 times negative 3 is positive 9. And then the right-hand side is 2x squared. Okay, so we'll combine all of the like terms. On the left-hand side, x squared plus x squared is 2x squared minus 2x minus 2x. So we're up to minus 4x, and then minus 3x minus 3x. We get a total of minus 10x. And then plus 4 plus 9 is plus 13. And then on the right-hand side, we just have 2x to the second. Both sides of the equation have 2x to the second, so we can subtract 2x to the second from both sides, and we're left with negative 10x plus 13 equals 0. And then we can do this in a couple of ways, whatever your preference is. I'll just subtract 13 from both sides to get negative 10x equals negative 13. And then when I divide both sides by negative 10, I get positive 13 tenths, because negative 13 divided by negative 10 is positive 13 tenths. Okay, if you struggle with solving equations with rational expressions, make sure you practice as much as you can. We have about 5 minutes, so let's see if we can solve this next one. X divided by x minus 4 minus 12x divided by x squared plus x minus 20 equals x minus 1 divided by x plus 5. Okay, the restricted values on this one are 4 and negative 5. So x can't be 4, and it's not allowed to be negative 5. And this is kind of nice because this denominator, x squared plus x minus 20, is just the product of x minus 4 and x plus 5. So the least common denominator is just x minus 4 times x plus 5 in factored form. But you can also write it in expanded form, x squared plus x minus 20. And then we multiply every term on both sides of the equation by the least common denominator. So we'll start on the left. So x minus 4 times x plus 5 over 1 times x over x minus 4. And then minus, this time I'll use the expanded form of the least common denominator, x squared plus x minus 20 over 1 times 12x over x squared plus x minus 20. And then on the right-hand side, we multiply x minus 1 over x plus 5 by the least common denominator. I'm going to use the factored form this time. X minus 4 times x plus 5 over 1 times x minus 1 over x plus 5. Okay, it looks worse before it looks better, but that's okay. In this first product, x minus 4 divided by x minus 4 equals 1, and we're left with x plus 5 times x. In the next product, x squared plus x minus 20 divided by x squared plus x minus 20, that equals 1, and we're just left with minus 12x. And on the right-hand side of the equation, x plus 5 divided by x plus 5 equals 1, and we're left with x minus 4 times x minus 1. Okay, so now we just do algebra and arithmetic. X plus 5 times x is x squared plus 5x, and then minus 12x. On the right-hand side, x minus 4 times x minus 1 is x to the second minus x minus 4x. And then negative 4 times negative 1 is positive 4, so we write plus 4. Okay, we're running out of time. Notice that both sides have x squared. The left-hand side, so we subtract x squared from both sides. And on the left-hand side, 5x minus 12x is negative 7x. And the right-hand side, minus x minus 4x is negative 5x plus 4. And we're just a couple of steps away. Add 5x to both sides, so we get negative 2x equals 4. And then divide both sides by negative 2. 4 divided by negative 2 is negative 2. And that is not a restricted value, so that's the solution. Okay, tomorrow we'll cover the next section, 8.4. And if there's time left tomorrow, we'll also look at Chapter 7 review problems. But that's all for today. Well, we'll go ahead and start. We'll review what we covered in section 8.3 yesterday. We covered the first part of this, but we'll go over it briefly again. So rational exponents. Radicals can be written in rational exponent form. A rational exponent is an exponent that is an ordinary fraction in lowest terms. And the properties of exponents that we learned in section 5.2 also apply to rational exponents. Here's a definition for converting radical form to rational exponent form. The nth root of a can be written as a raised to the exponent 1 over n. And remember that the denominator of the exponent is the same number as the index of the radical. Okay, we'll convert from radical form to rational exponent form in a few examples. The square root of x. The index of a square root is 2. So when we convert the square root of x to rational exponent form, it's x to the 1/2 power. The cubed root of 15, the index of the radical is 3. So the denominator of the exponent will be 3. So 15 to the 1/3 power is equivalent to the third root of 15 in radical form. The fourth root of n converted to rational exponent form, it's n to the exponent 1/4. The denominator of the exponent is the same as the index of the radical. And then the fifth root of 11 converted to rational exponent form, that's 11 to the 1/5. Here we'll do it in the opposite order this time. We have these terms that are in rational exponent form, and we'll convert them to radical form. 17 raised to the exponent 1/2 in radical form. The denominator of the exponent is 2, so that means the index of the radical is 2, and the number that's inside the radical is 17. Since it's a square root, or a radical with index 2, it's a square root, so the index doesn't need to be written, but you can write it. A to the 1/4, the denominator of the exponent is 4, so the radical has index 4, and the radicand is a. 29 to the 1/6, the denominator of the exponent is 6, so the radical has index 6, and the number inside the radical is 29. Y to the 1/3, well, the denominator this time, the denominator of the exponent is 3, so this is just the cubed root of y, or the third root of y, if you want to think of it that way. In the following examples, we'll simplify the expressions that have rational exponents. And in each of these examples, we can simplify without converting them to radical form. 49 to the 1/2, that's just the square root of 49, and the square root of 49 is 7. If you want to convert it to radical form, you can, but it's not required. 49 to the 1/2 is the square root of 49, and we know that the square root of 49 is 7. 81 to the 1/4, well, you might remember that 81 is a perfect fourth power. 3 to the 4th is 81, so 81 to the 1/4 power is just 3. I'll remind you of a property of exponents that we can apply in this case. Once again, it's not required, but it's nice to know that you can do this. We know that 81 is 3 to the 4th. So if I replace 81 with 3 to the 4th, and I have 3 to the 4th raised to the 1/4 power, we have a property of exponents that says we can multiply the outer exponent 1/4 by this exponent, and 1/4 times 4 is 1. So this just simplifies to 3 to the 1st power, or 3. Okay, the property of exponents that I applied here, I'll remind you, from section 5.2, we learned that if you have a raised to the power m, and if that is raised to the power n, you can multiply the exponents and write it as a to the m times n. And that's what I did in this case. 1/4 times 4 is 1, and 3 to the 1st power is 3. Okay, the next example, simplify 32 to the 1/5. 32 is a perfect 5th power. And so hopefully we know automatically that 32 to the 1/5 simplifies to 2. But you can use a little more detail if you want. 32 is equivalent to 2 to the 5th. So 32 to the 1/5 is 2 to the 5th to the 1/5, and then 1/5 times 5 is 1, and 2 to the 1st is just 2. And the next example on this page, 64 to the 1/3. 64 is a perfect 3rd power because 4 to the 3rd power is 64. So this just simplifies to 4. The 3rd root, or the cube root of 64, is just 4. Or you can write 64 as 4 to the 3rd. And so 64 to the 1/3 is equivalent to 4 to the 3rd raised to the 1/3. And then use this property of exponents down here again. Multiply the exponents. 1/3 times 3 is 1, and we get 4 to the 1st power, or 4. Okay, we'll move on to the next sheet. We have another definition related to the first definition that we saw on this page. This also involves converting from radical form to rational exponent form. This is a little more complicated, not much. This time we let m and n be positive integers, and the nth root of a to the m is a to the m raised to the 1/n. This is just an application of the definition that we saw on the previous page. And then using that property of exponents that we reviewed, if you multiply the outer exponent 1/n times m, you can write this as a to the m/n. And also using the same property of exponents, well, we know that m times 1/n is the same as 1/n times m. So we can rewrite it so it looks like this. Inside the parentheses, we have a to the 1/n, and that's raised to the power m. And then on the inside of the parentheses, if you convert a to the 1/n to radical form, it's the nth root of a inside the parentheses raised to the exponent m. These 5 terms are equivalent. Oftentimes we're not going to use all of those, but it's nice to know that you can if you have to. We'll look at some examples where we convert from radical form to rational exponent form. The 7th root of x to the 4th. We can first write in parentheses x to the 4th because that's what's inside the radical. And then the index of the radical is 7, so this is raised to the exponent 1/7. And then if we multiply the exponent 1/7 times 4, we can write it as x to the 4/7. The next one, the fourth root of the term 2y. So this time 2y is in parentheses, and when we convert it to rational exponent form, the exponent is 1/4. So we're going to think of 2 as 2 to the first and y as y to the first. And then we'll apply one of the properties of exponents. Up here, I'll remind you of the property that we're going to look at. If you remember from section 5.2, if you have a times b raised to the power m, thinking of a as a to the first and b as b to the first, you can multiply the exponent m times each of those and write it as a to the m times b to the m. Okay, that's what we're going to do in this case. The term 2y is raised to the 1/4, so we can write it as 2 to the 1/4 times y to the 1/4. And if all we are doing is converting it to rational exponent form, then there's nothing more to do on this one. Okay, the next example, the fifth root of 12 times w to the second. Convert it to rational exponent form. So inside the parentheses, we'll write 12w to the second, and the outer exponent is 1/5. And this is 12 to the first times w to the second. So we'll just multiply 1/5 times the exponents on the factors, and we get 12 to the 1/5 times w to the 2/5, because 1/5 times 2 is 2/5. Okay, we'll convert from rational exponent form to radical form this time. So this one, x to the 3/4, the denominator of the exponent is 4, so that means the index of the radical is 4. So when we convert it to radical form, we put the index 4, and then we can write x to the 3rd on the inside. If you want to use put it or use more detail, you can. It's not required, but if you want to think of x to the 3/4 as x to the 3rd to the 1/4, and then convert this to radical form, we get the same result. It's the 4th root of x to the 3rd. Okay, the next two terms, they sort of look similar, but they mean something different. The middle one, 5 times y to the 2/3. The exponent 2/3 applies to y only. It doesn't apply to the coefficient 5. So when we convert this to radical form, 5 has to stay outside of the radical. And the radical has index 3 because the denominator of the exponent is 3. And then on the inside, we have y to the 2nd. This third term on the right, this means something different. Since 5y is in parentheses and the exponent is 2/3, the exponent 2/3 applies to 5 to the first as well as y to the first. Okay, so the denominator of the exponent is 3. So we'll write the radical with index 3. And this is where you'll want to make sure you're careful. We can write on the inside of the radical, the term 5y in parentheses with the outer exponent 2. This is a perfectly fine way to convert it to radical form. But you can also square 5y, because 5y in parentheses to the second power means that you're multiplying 5y times 5y, which is 25y to the second. If you write the term 5y without parentheses and the exponent 2, that is incorrect, because this outer exponent 2 applies to the factor 5 as well as to the factor y. So this is one of those things that you have to be careful about. Okay, let's evaluate the numbers with rational exponents. Starting on the left, the number negative 16 raised to the exponent 1/4. Well, you might remember from section 8.1, before we talked about rational exponents, if you have a index of a radical that is even, such as 4, and if the radicand is a negative real number, then that root is not a real number. So this is not a real number, because we're raising the number negative 16 to the exponent 1/4. Written in radical form, it's the 4th root of negative 16. And just to reiterate, in section 8.1, whenever the index of a radical is even, such as 2, 4, 6, 8, 10, and so on, and if the number inside the radical is a negative real number, such as negative 16, then that is not a real number. It is a number, it's just not a real number. So we have to know when to identify such a thing as not being a real number. So not a real number. Okay, the next one looks sort of similar to the one on the left, but it's different. This means the negative of 16 to the 1/4. So it's not often done, but negative 16 to the 1/4 can be thought of as the number negative 1 times 16 to the 1/4. So technically the exponent 1/4 applies to positive 16. And we're just taking the negative of 16 to the 1/4. It's a little bit easier to see if you write it in radical form. You put the negative symbol on the outside, multiply, or take the negative of the 4th root of 16. The 4th root of 16 simplifies to 2. So this simplifies to negative 2. Okay, the next example, the number 16 raised to the exponent negative 1/4. Okay, so if we have a negative exponent, such as in this case 16 to the negative 1/4, this is 1 over 16 to the positive 1/4. The 16 to the positive 1/4 is in the denominator. And 16 to the 1/4 is equal to 2, so this just simplifies to 1/2. And the next example is similar in a way to the one we just did, 32 to the negative 2/5. Well, we want to write that as 1 over 32 to the positive 2/5. And 32 is a perfect 5th power. So oftentimes you can just compute these in your head, but I'll rewrite this using our definitions and properties of exponents. In the denominator, 32 to the 2/5 is equivalent to having 32 to the 1/5 in parentheses and an outer exponent of 2. And then inside the parentheses, 32 to the 1/5 simplifies to 2 because 32 is a perfect fifth power. So this becomes 1 over 2 to the second, and 2 to the second is 4, so we just get 1/4. I'll point out another thing about this example. Notice that the positive number 32 raised to a negative exponent is still a positive number. The exponent being negative has nothing to do with the sign of the base number. The base number can be positive or negative. Okay, we'll move on to the next page. So on this page, we're just going to apply properties of exponents to the expressions with rational exponents. And we're not going to convert to radical form. The directions don't say to convert it to radical form. So we're just going to apply properties of exponents and simplify. And in the process, I'll remind you of some of the properties of exponents that we learned in section 5.2. Okay, so this first one, we're multiplying x to the 1/6 times x to the 4/3. So we're going to apply the property of exponents that says we can write x once and add the exponents. So up here, I'll write the property as we saw it in section 5.2. If I can write. So this is supposed to be all this over, a to the m times a to the n. If you have a to the m times a to the n, we can write it as a to the m plus n. Okay, that's what we're going to do in this case. X to the 1/6 times x to the 4/3 is x to the 1/6 plus 4/3. And then we have to add the fractions and the exponent. Before we can add fractions, we have to have a common denominator. So we'll add 1/6 to 8/6. And 1/6 plus 8/6 is 9/6. And we always want to write fractions in lowest terms. So the exponent 9 over 6 simplifies to 3 over 2. That is our simplified result. We're not converting these to radical form. Okay, the next one, we've seen the property that applies here a couple of times. X to the 6th raised to the 4/3. This time we're just going to multiply the exponents. So 4/3 times 6. So we can write it as x to the 6 times 4/3. And then you can write it as x to the 24/3, because 6 times 4/3 is 24/3. And 24/3 simplifies to 8. So our simplified result is x to the 8th. Okay, in the next example, x to the 2/3 divided by x to the 5/3. Well, up here on the top, I'll remind you of the property that we're going to use this time. If we have a to the m divided by a to the n, we can write it as a to the m minus n. If you write it this way, it's important to remember that a to the m minus n is in the numerator, and you don't need to write a fraction bar over 1. But if it helps you to remember, then by all means go ahead and write it. But there's another way to write what a to the m divided by a to the n is, and that is to write it as 1 over a to the n minus m. Okay, either of those two properties will work in the end if you know how to handle negative exponents. Okay, so let's work on this one. We can go about simplifying this in more than one way. If we just do the one option, we can write this as x to the 2/3 minus 5/3 over 1, but I won't write it over 1. And then 2/3 minus 5/3 is negative 3/3. And negative 3/3 is negative 1, so we get x to the negative 1. But we don't want to end with any negative exponents. So x to the negative 1 is 1 over x to the positive 1, or just 1 over x. Okay, that is a perfectly fine way to get to the end result. As long as you apply the appropriate properties, you can get to the end result. But maybe a shorter way to do it, I'll do that down here. X to the 2/3 divided by x to the 5/3. I note that the exponent on x in the denominator is a bigger number than the exponent on x in the numerator. So that observation leads me to write it as 1 over x to the 5/3 minus 2/3. That's the alternative way that I wrote down a little bit earlier at the top of this page. And then the exponent 5/3 minus 2/3 is positive 3/3. And 3/3 is 1, so we just get 1 over x to the positive 1, or just 1 over x. So as you can see, either way gets you to the end result. Just apply appropriate properties of exponents. Okay, and the next one, x to the 3/4 times y to the 1/2, that entire product is raised to the 2/3. So above that here, I'll just write down a property that applies to this one. If you have a times b to the m, thinking of a as a to the first and b as b to the first, or they could be any other exponents besides 1, then we can multiply m times each of those exponents and write it as a to the m times b to the m. Okay, so we apply that one. We're going to multiply the outer exponent 2/3 times the exponent 3/4 on x, and we will also multiply 2/3 times the exponent 1/2 on y. So we get x to the 3/4 times 2/3, and then times y to the 1/2 times 2/3, and then just do the arithmetic. So 3/4 times 2/3 is 6/12, and that simplifies to 1/2. And then y to the 1/2 times 2/3, 1/2 times 2/3 is 2 over 6, but that simplifies to 1 over 3. So our simplified answer is x to the 1/2 times y to the 1/3. So if you're wondering why I sometimes write division bars horizontally, and at other times I write them slanted. The answer is I don't know. Okay, in the next example, we have 32 times x to the 1/3, and that entire expression is raised to the 3/5. So think of 32 as 32 to the first, and we will apply the same property that we did in the previous example. We'll multiply the outer exponent 3/5 times the exponent 1 on 32 and the exponent 1/3 on x. Okay, so we'll get 32 to the 3/5 times x to the 1/3 times 3/5. And 32 to the 3/5 is going to simplify nicely. But in the interim, we'll rewrite 32 to the 3/5 as 32 to the 1/5 in parentheses with an outer exponent 3. And then we'll go ahead and simplify what x to the 1/3 times 3/5 is. So the exponent is 3 over 15, and that simplifies to 1/5, 1 over 5. Okay, we saw this a little earlier today. 32 to the 1/5 is 2, because 32 is 2 to the 5th. 32 is a perfect fifth power. So this becomes 2 to the 3rd, and then times x to the 1/5. And then 2 to the 3rd can be simplified as 8. So our simplified result is 8 times x to the 1/5. Okay, and the next one, 343 to the 2/3. Well, if you can remember that in this course, things work out nicely. Notice that the denominator of the exponent is 3. And 343 is a perfect cube, or a perfect third power. 7 to the 3rd is equal to 343. Okay, so you can go about simplifying this in a couple of equivalent ways. So if you make that observation, that 343 is 7 to the 3rd, and the denominator of the exponent is 3, then that's going to indicate that we're going to get a nice cancellation in the process. So I'm going to replace 343 with 7 to the 3rd, and then the outer exponent is 2/3. And then 7 to the 3rd raised to the 2/3 is 7 to the 3 times 2/3. But 7 to the 3 times 2/3 is 7 to the 2nd. And 7 to the 2nd is 49. Okay, so that simplifies to 49. Alternatively, we can write 343 to the 2/3 as 343 to the 1/3 raised to the exponent 2. And 343 to the 1/3 is just 7, because 343 is a perfect cube. So we get 7 to the 2nd, or 49. Okay, often there are multiple ways about simplifying expressions, but they never involve breaking the rules. So make sure that you know the rules. Okay, that gets us through the material in section 8.3. We're going to start section 8.4. So in 8.4, We're going to consider operations with radical expressions. We'll first start out by adding and subtracting radicals, and then the second part of section 8.4 has to do with multiplying radicals. Okay, so let's read this paragraph. Like radicals can be combined by adding and subtracting the same sort of way that you would combine regular like terms by adding and subtracting. So simplified radicals are called like radicals if their indexes, variable parts, and radicands are the same. Like radicals may have different numerical coefficients. In the same way that like terms have different coefficients, then like radicals can also have different coefficients. So what you'll want to make sure that you do before you start adding and subtracting, you want to make sure that the radicals are as simplified as much as possible. In this first example, 11 times the square root of 3 minus 7 times the square root of 3. The square root of 3 is as simplified as it can be, and the square root of 3 appears in both terms, so we can combine this by subtraction. In the same sort of way that you can simplify 11x minus 7x to equal 4x, then that applies here because these are like radicals. 11 times the square root of 3 minus 7 times the square root of 3 simplifies to 4 times the square root of 3. It's pretty simple, really. The next example, 5 times the square root of x plus 3 times the square root of x minus the square root of x. Each of the radicals, each of the square roots is as simplified as much as possible. And each of the radicals is exactly the same as the other ones. So these are like radicals, and they can be combined by adding and subtracting. So 5 times the square root of x plus 3 times the square root of x, those add up to 8 times the square root of x. But then when we subtract the square root of x, we just have a total of 7 times the square root of x. Okay, the next example. Okay, over here on the left, 14 times y times the cubed root of 9x plus 11 times y times the cubed root of 9x. The cubed root of 9x cannot be simplified any further, and the cubed root of 9x appears in both terms. But each of the terms also has a factor of y on the outside of the radical. And the only difference are the coefficients, but that's okay. These are like terms that can be combined by adding. So 14 times y times the cubed root of 9x plus 11 times y times the cubed root of 9x, those add up to give us 25y times the cubed root of 9x. That's the simplified result. Okay, the next one, 13 times m times n times the fourth root of 7r minus 10 times m times n times the fourth root of 7r. The fourth root of 7r cannot be simplified any further. And each of the terms has a factor of m and a factor of n on the outside. So these are like terms, and they can be combined by subtracting. Okay, so 13mn times the fourth root of 7r minus 10 mn times the fourth root of 7r. That simplifies to 3 mn times the fourth root of 7r. Okay, I'm sure that you understand what's going on, but we'll do these last two anyway. 19x squared times the fifth root of 12y to the third minus 3x squared times the fifth root of 12y to the third. The fifth root of 12y to the third cannot be simplified any further. And each of the terms has x squared on the outside. So those are like terms, and so we can combine them by subtracting. So I have 19 of those minus 3 of the same, so we get a total of 16x to the second times the fifth root of 12y to the third. Okay, in the next example, so notice the seventh root of 11c cannot be simplified any further. Both of the terms have the seventh root of 11c, and outside of the radical, both terms have a factor of a to the fourth, and they also have a factor of b to the fifth. So these are like terms that can be combined by adding. So negative 7 of those plus 10 of the same adds up to 3 times a to the fourth, b to the fifth, times the seventh root of 11c. That's the simplified result. Okay, the remaining 8 or 9 minutes, we'll start looking at the more complicated situations. What follows is we'll be adding and subtracting radicals, but the radicals won't be simplified like they were in these 6 examples. Okay, simplify the radicals, then combine like radicals by adding and subtracting. So in this first one, 2 times the square root of 75 minus 9 times the square root of 48. Well, each of those square roots can be simplified further. The largest factor of 75 that's a perfect square is 25. So this can be thought of as 2 times the square root of 25 times the square root of 3, because 25 times 3 is 75. And then minus the largest factor of 48, that's a perfect square, is 16. 16 times 3 is 48. So we can write this as minus 9 times the square root of 16 times the square root of 3. And the square root of 25 is 5. So I'll start to abbreviate a little bit because you no doubt see what's going on. The square root of 25 is 5, and 2 times 5 is 10. So I'm just going to have 10 times the square root of 3. And then minus 9 times the square root of 16 times the square root of 3. The square root of 16 is 4, and minus 9 times 4 times the square root of 3 is minus 36 times the square root of 3. And then the 2 radicals are alike, so we can combine by subtracting. 10 times the square root of 3 minus 36 times the square root of 3 is negative 26 times the square root of 3. That's the simplified result. Okay, in the next example, 2 times the square root of 45 plus 5 times the square root of 48 minus 3 times the square root of 20. Each of the square roots can be simplified. The largest factor of 45, that's a perfect square, is 9. So we have 2 times the square root of 9 times the square root of 5. 9 times 5 is 45. The largest factor of 48, that's a perfect square, is 16. So this is plus 5 times the square root of 16 times the square root of 3. And then this, the largest factor of 20, that's a perfect square, is 4. So we can write this as minus 3 times the square root of 4 times the square root of 5. The square root of 9 is 3, and 2 times 3 is 6. So this gives us 6 times the square root of 5. The square root of 16 is 4, and 5 times 4 is 20, so we get plus 20 times the square root of 3. And the square root of 4 is 2, so minus 3 times 2 times the square root of 5 is minus 6 times the square root of 5. Okay, notice that the square root of 3 is a different radical than the square root of 5. But 6 times the square root of 5 minus 6 times the square root of 5, those combine to give us 0. And so the simplified result is 20 times the square root of 3. But keep in mind that if we were to just add the first two terms, they cannot be added because they are not like radicals. Okay, the next example, 4 times the square root of 18xy to the second plus the square root of 8xy to the second minus 5y times the square root of 50x. Each of those square roots can be simplified further. So on the left, we'll write 4 times the square root of the perfect square factors, which are 9y to the second, and then multiplied by the square root of the remaining factors, which are 2 times x. And then the middle term, the largest factor of 8 that's a perfect square is 4, and y squared is a perfect square. So we can write this as plus the square root of 4y to the second multiplied by the square root of the remaining factors. The remaining factors are just 2 times x. And then minus 5 times y. We can simplify the square root of 50x. The largest factor of 50 that's a perfect square is 25. So we can write this as the square root of 25 times the square root of 2x. And we'll do a shortcut or two. The square root of 9y to the second is 3y, and 4 times 3y is 12y. So we have 12y times the square root of 2x. The square root of 4y to the second is 2y, so we have 2y times the square root of 2x. The square root of 25 is 5, so minus 5y times 5 times the square root of 2x is minus 25y times the square root of 2x. Okay, so each of the radicals that have been simplified are identical. They each are the square root of 2x. But the variable parts on the outside also have to be the same, and they are all the same, so we can combine by adding and subtracting. So we have 12 of those objects added to 2, and then minus 25. So altogether, we just have a negative 11y times the square root of 2x. Okay, the next one, we have a little over a minute left, but we can start. These involve cubed roots. The cubed root of 16m, that can be simplified. The largest factor of 16 that's a perfect cube is 8. So we'll rewrite this as the cubed root of 8 times the cubed root of 2m. And then in the next term, the largest factor of 54, that's a perfect cube, is 27. 27 times 2 is 54. So we can write this as 5 times the cubed root of 27 times the cubed root of the remaining factors, which are just 2m. And then the largest factor of 40, that's a perfect cube, is 8. 8 times 5. So this is 2 times the cubed root of 8 times the cubed root of 5m. Okay, we'll stop here, but just note that this third term is not a like term with the other two. Okay, we'll pick it up tomorrow on this problem. That's all for today.